In our last video, we have studied direct method for testing of DC machines. We have seen that direct method gives most accurate result, and we can also check conditions like temperature rise, commutation, etc. during actual loading condition with the help of direct testing method. However, direct testing method is not suitable for large machines. For testing of large machines, we have to use indirect method or regenerative method. In this video, we will learn Swinburne's test, which is indirect method for testing of DC machines. Let us now see what is the procedure of Swinburne's test. So Swinburne's test, it is an indirect method of testing of DC machines. In indirect method of testing, the machine is not actually loaded up to full load. But without actually loading the machine, we can determine its losses and efficiency for any load condition. So in this method, the machine is always run as a motor at no load. So here the machine, whether it is generator or it is motor, it is always run as a motor at no load. And therefore the method is also known as no load test. So this Swinburne's test or indirect method, it can be applied in case of shunt machines or flat compounded DC machines. In these machines, speed is almost constant from no load to full load, and the field current is also constant from no load to full load. Now this method we cannot apply for series machines because you know that series motor cannot be operated at no load. If it is operated at no load, its speed may become dangerously high and it may get damaged. And therefore, this method is suitable for shunt machines or flat compounded machines where field current is constant from no load to full load. Now as the speed is constant, we can assume that mechanical losses as constant. So we can assume friction and windage losses as constant because speed is constant. Then in these machines, field current is also constant from no load to full load. And as field current is constant, flux is also constant. And if flux is constant, we can assume that core or iron losses to be constant. So in this method, we are operating the machine at no load and the machine is operated at rated voltage and rated speed. And that's why we can assume that mechanical losses and core or iron losses as constant. Now in this method, first of all, we have to start the machine as a motor. So we have to connect the circuit as per diagram, and then we have to close the main switch. Then with the help of starter, we have to start the machine. We have to adjust the voltage at rated voltage. So this voltage must be equal to rated voltage, and speed of the machine N is also adjusted at rated speed, and this speed adjustment can be done with the help of this field rheostat R. So after operating the machine at no load with rated voltage and rated speed, we have to note down the supply voltage V, no load current drawn by the motor, and field winding current ISH flowing through the field winding. And with these three readings, we can determine losses and efficiency of the machine for any operating condition. Now we have studied the procedure of performing Swinburne's test. With the help of readings of Swinburne's test, it is possible to determine constant losses of the machine. Once the constant losses are determined, it is possible to determine the efficiency of machine at any load condition, whether the machine is operating as a generator or as a motor. So let us now see what is the procedure for determination of constant losses. So here let V is equal to the supply voltage in volts. So you know that in Swinburne's test, this voltage is always adjusted to rated value. Then let I0 is the no load input current of the motor in ampere. So in Swinburne's test, the machine is always operated as motor and it is operated at no load. So I0, it is the no load input current of motor in ampere. Then let ISH, it is the current drawn by the shunt field winding in ampere, and IA0, it is the current drawn by armature at no load. So here I0, it is incoming current, ISH, it is outgoing, and IA0, it is also outgoing, and therefore IA0, it must be equal to I0 minus ISH. So current through armature IA0, it is I0 minus ISH. Now here no load input power. So this input power to the motor Pin, it is equal to V into I0. Here V is the supply voltage and I0 is the input current at no load. Now in case of any machine, input power is always equal to output power plus losses. Now here the machine is operating at no load and therefore this output power, it is equal to 0. And if output power is equal to 0, then input power, this input power, it must be equal to losses, and therefore input power, it is equal to losses. And you know that there are two types of losses: constant losses and variable losses. So these constant losses include mechanical loss, that is friction and windage loss, plus iron loss, plus loss of power in shunt field winding. Whereas variable loss is loss of power in armature. So here variable loss is equal to armature copper loss, and armature copper loss is Ia0 square into Ra, where Ra, it is the resistance of armature. So loss of power in armature, it is Ia0 square into Ra. And as Ia0 is equal to I0 in minus ISH, it is I0 minus ISH square into Ra. So if this variable loss is subtracted from input power, we will get constant loss, and therefore constant loss, that is W constant. This W constant, it is equal to input power minus variable losses. So input power is nothing but V into I0, and variable losses, it is I0 minus ISH square into Ra. So with the help of Swinburne's test, we can calculate constant losses as Vi0 minus I0 minus ISH bracket square into Ra. So with the help of readings of Swinburne's test, it is possible to determine constant losses of the machine. Now using these constant losses, it is possible to calculate the efficiency of machine at any load, whether the machine is working as a generator or as a motor. So for motor as well as generator, at any load condition, it is possible to calculate the efficiency once we know constant losses, that is W constant. And these constant losses, W constant, can be calculated using this expression. Now we have studied the procedure of calculation of constant losses, W constant. Let us now see how to calculate the efficiency of machine when the machine is running as a motor. So here let V, it is equal to supply voltage in volts. Then let IL, it is the current drawn by the motor, that is load current in ampere at which efficiency is required. Now here ISH is the current flowing through the shunt field winding, and IA is the current flowing through armature. So here the power input to the motor is electrical power input, and this electrical power input P in, it is equal to the product of supply voltage V and load current IL. So P in, it is equal to V into IL. Now armature current IA, it is equal to IL minus ISH. So here IL is the load current, which is incoming current for this junction, and IA and ISH both are outgoing currents, and that's why IA, it is equal to IL minus ISH. Now armature copper loss, which is nothing but variable loss. So this armature copper loss, it is equal to Ia square Ra, and Ia, it is equal to IL minus ISH, and that's why variable loss in the machine, it is IL minus ISH bracket square into Ra. Now total loss, it is variable loss plus constant loss, and constant loss is already calculated as W constant, whereas variable loss is copper loss taking place in armature, and therefore total loss, it is constant loss plus variable loss. Now if you know total losses, it is possible to calculate the efficiency. You know that efficiency, it is output power divided by input power. And for any machine, output power, it is equal to input power minus losses. So here input power is nothing but V into IL, and losses are equal to constant losses and variable losses. And that's why efficiency of motor can be calculated as VIL minus W constant minus IL minus ISH bracket square RA divided by VIL into 100 if you want the efficiency in percentage. So percentage efficiency of motor can be calculated using this expression. Let us now see how to determine the efficiency if the machine is running as a generator. So here let V, it is the terminal voltage of generator in volts, and IL, it is the load current at which efficiency of generator is required. So current drawn by load, it is IL, and voltage across load, it is equal to V. And therefore electrical power output of generator P out, it is equal to terminal voltage V multiplied by load current IL. So output power of generator, it is equal to VIL watt. Now in case of generator, power input, it is mechanical and power output is electrical. Now during this energy conversion, various losses will occur, and these are constant losses plus variable losses. Now variable loss will occur in armature. Now here armature current IA, it is equal to IL, that is load current, plus ISH, that is shunt field winding current. So here for this junction, IA is the incoming current, ISH, it is the outgoing current, and IL, it is also outgoing current. And that's why IA, it is equal to IL plus ISH. And therefore armature copper loss, which is equal to variable loss, which is equal to IA square RA, which is IL plus ISH bracket square into RA. And you know that total loss, it is equal to constant loss plus variable loss. Now constant loss is already determined as W constant, and variable loss is nothing but armature copper loss. So if you know total losses, it is possible to determine the efficiency. So efficiency of generator, it is equal to output power divided by input power. So it is equal to output power divided by output power plus losses. And therefore efficiency is nothing but output power, that is VIL, divided by output power, that is VIL, plus losses, that is constant loss W constant plus variable loss IL plus ISH square into RA multiplied by 100 if you want percentage efficiency. So percentage efficiency of generator can be determined using this expression. Let us now solve one numerical problem on Swinburne's method. Let us first of all see what is the given data. So a 250 volt 200 kilowatt DC shunt motor means type of machine is shunt and rated power it is equal to 200 kilowatt, which is equal to 200 into 10 raised to 3 watt. Then the results of tests are when running light. Running light means the machine is operating at no load. So when the machine is operating at no load, the line current was 36 ampere. Means I0 it is equal to 36 ampere. So this current drawn by motor at no load I0 it is equal to 36 ampere. Field current 12 ampere means this current ISH it is equal to 12 ampere and supply voltage 250 volt. So V is equal to 250 volt, which is equal to the rated voltage. So this V it is equal to 250 volt. So these three readings are given. I0 it is 36 ampere, ISH is 12 ampere and V is equal to 250 volt. Then second test reading is with the machine at rest, a potential difference of 6 volt produced a current of 400 ampere in the armature circuit. So this data is useful to determine the armature resistance Ra. So when voltage applied across armature is 6 volt, then the current of 400 ampere is flowing through armature and therefore armature resistance Ra it is voltage applied across armature that is 6 volt divided by current through armature that is 400 ampere, and if you solve this 6 upon 400 it is equal to 0.015 ohm. So resistance of armature this Ra it is equal to 0.015 ohm. So with these readings, first step is to calculate the constant losses, that is W constant. So for that, first of all we have to calculate what is the no load input power, and as studied earlier, no load input power is nothing but total losses, because here output is equal to 0 because the machine is operating at no load, and that's why no load input power is equal to total losses, which is equal to V into I0. V is 250 volt and I0 is 36 ampere. So if you solve this, input power it is equal to 9000 watts. Now from these total losses, if variable losses are subtracted, we will get constant loss. So variable loss it is equal to armature copper loss, which is equal to Ia0 square into Ra. Now Ia0 is nothing but I0 minus ISH. So this current is incoming, which is I0, ISH is outgoing and Ia0 is also outgoing, and that's why Ia0 is equal to I0 minus ISH, that is 36 minus 12, which is equal to 24 ampere. So Ia0 it is 24 ampere, and that's why variable loss is 24 square into 0.015, which is equal to 8.64 watt. Now using these variable losses, we can calculate constant loss. So constant losses, W constant, it is equal to total losses minus variable losses. Now total loss is 9000 watt and variable loss is 8.64 watt, and therefore 9000 minus 8.64, it is equal to 8991.36 watt. So now we have calculated constant losses W constant. Now these will remain constant from no load to full load. Now using these constant losses, we have to calculate the efficiency of generator at full load and also at half load. Now constant losses are calculated as W constant is equal to 8991.36 watt. Now using these constant losses, we can calculate the efficiency at full load and half load. Let us first of all consider full load condition. So when the machine is fully loaded, its output is equal to rated value. That is rated output power, it is 200 kilowatt. And terminal voltage, it is 250 volt. So using this power and voltage, we can calculate the full load current. So I full load, it is equal to 200 into 10 raised to 3 divided by 250, which is equal to 800 ampere. So full load current is 800 ampere. Now the current through armature, it is IFL plus ISH. Now IFL, it is 800 and ISH, it is 12, and therefore 800 plus 12 and IA, it is 812 ampere. Now variable loss, it is equal to IA square RA. So it is 812 square into 0.015, which is 9890.16 watt. And therefore total loss, it is equal to constant loss plus variable loss, which is 8991.36 plus 9890.16, which is equal to 18881.52 watt. Now with the help of these total losses, we can calculate efficiency at full load, which is output power divided by output power plus losses into 100. So it is 200 into 10 raised to 3 divided by 200 into 10 raised to 3 plus 18881.52 multiplied by 100. So full load efficiency is 91.37%. Similarly, we can calculate efficiency at half load. Now when the generator is at half load, its electrical power output will be 100 kilowatt and terminal voltage is 250 volt. So with these two values, we can calculate half load current. So half load current is 100 into 10 raised to 3 divided by 250, which is 400 ampere. So current at half load, it is 400 ampere and ISH is 12 ampere, and therefore IA, it is the sum of IHL and ISH, that is 400 plus 12, which is 412 ampere. So IA is 412 ampere, and therefore variable loss, it is 412 square into 0.015, which is 2546.16 watt. Constant loss will remain same, and therefore total loss is constant loss, that is 8991.36 plus variable loss 2546.16, which is 11537.52 watt. Using these total losses, we can calculate efficiency at half load, which is output power upon output power plus losses. So 100 into 10 raised to 3 divided by 100 into 10 raised to 3 plus losses, that is 111,537.52 multiplied by 100. So solving this, we will get efficiency at half load, which is 89.66%. So with the help of Swinburne's test, we can determine the efficiency at any load, whether the machine is working as generator or as motor. Let us now see what are the advantages and disadvantages of this method. The first advantage is the method is very simple and it is also economical, because the power required for testing is only no load power, and which is very less. Then the second advantage is, with the help of this method, it is possible to test large machines without actually loading the machine up to full load. Then the third advantage is, we can determine the efficiency of machine, whether it is working as generator or as motor, and at any load condition. But the disadvantages of the method are, in this method, it is not possible to check actual loading conditions, like what is the effect of temperature rise, what is the effect of loading on commutation, that is sparking at brushes, etc. So all these operating conditions during actual loading cannot be checked by this method. Then with the help of this method, it is not possible to test series machines, because series motor cannot be operated at no load. Then in this case, we are not actually loading the machine, and therefore effect of armature reaction on actual loading condition cannot be taken into account. And the fourth disadvantage is, this method gives only approximate results. With the help of direct loading test, we get accurate results, whereas here the results are not accurate like direct loading test, but we get approximate results only. So we have studied direct and indirect method for testing of DC machines. In our next video, we will study regenerative type test, that is Hopkinson's test. Thank you.